So you guys saw about Lenz's law, right? See, now one simple question. See, we are getting some EMF from the coil, correct? Because of the change in magnetic field. Now, how do we know what is the magnitude of the EMF induced in the coil? Because every EMF and current, basically, current and EMF, we should have some sort of value, magnitude, correct? Now, to find the magnitude of it, so this is quite an important part. This is what we call as the motional EMF. Okay, so motional EMF. So you're moving an object, like it could be the magnet or it could be the coil, any one of it. So you're moving it. What is the EMF induced in the particular coil? Okay, now for this derivation, so what we are going to do, like the setup of this particular experiment, we have into the field, into the plane, basically magnetic field. Okay, and then we have a coil. So the coil is connected to the galvanometer, basically to measure the EMF. All right. So now what we'll use, we will use the Lorentz force, and to find the direction of it, we use the Fleming's left hand rule. Okay, these are the things what basically is needed here. So what we have is initial stage, we have into the plane magnetic field, and we have a coil, so call it as ABCD. Okay, it's connected to the galvanometer G. Okay, now what we have, see, we have into the plane. So if you use your Fleming's left hand rule, so you have force, field and current, right? Now we have to pull the coil towards one direction to figure out what is the direction of the EMF, correct? Because as you change the direction, EMF direction also changes. We saw that in the Lenz's law, right? Okay, so let's say this is the direction in which you are moving. So if you apply Fleming's left hand rule, so force, field and current, so this will be the direction of the current, basically the EMF, right? Okay, see, now you have A, B, C, D is the coil. Now let's say the length of the particular coil which is in the magnetic field, let's call it as X. Okay, and the breadth of the coil, let's call it as L. So you have, this is X and this is L, right? So now as you keep moving the coil away from the magnetic field, so what happens? X value changes, correct? L will not change, L remains the same, X will change. So let's call A dash B, C, D dash. So let's call this is the rectangle which is there in the particular magnetic field. Okay, now, so first thing what we have is, see, the coil is moving, correct? So that means X changes. Again, I'm repeating this point because as X changes, time also changes, right? So what we are looking at is, we are looking at phi. Okay, the magnetic flux linking with the coil. The formula was B into ds, correct? So in this case, B into ds. So in this case, ds is nothing but the area of the rectangle, which is L times X. So we got phi is equal to BLX. Okay, now induced EMF is given by what? d phi by dt we need to calculate, right? So d phi by dt becomes BL into dx by dt. Now why dx by dt? Because X changes. This is the reason I was stressing that X changes every time. Okay, so we have BL dx by dt. Dx by dt is nothing but velocity, because X is the displacement. So displacement by time gives you velocity. So we got d phi by dt as BLV. Now the induced EMF is given by E is equal to minus d phi by dt, which gives you the induced EMF as minus BLV, so many volts. Okay, now this is the expression for the induced EMF in a coil. Okay, I'll just go through this quickly again. So what you have is, you have a coil, you have a magnetic field. The length of the coil in the magnetic field is X, the breadth of the coil is L. You move the coil, so X changes with respect to time. So the magnetic flux will be B into ds, that's basically BLX, and then as you keep moving the coil, so we have to take the derivative of phi, so d phi by dt becomes BLV, and then induced EMF becomes minus BLV. So this is the EMF, correct? Now coming to the current induced. So the current will be E divided by R, where R is the resistance of the coil. So you have minus BLV divided by R. Understood? So this is the current, that's the EMF. Now in the next video, you will see one more type of motional EMF. See here the motion was linear, correct? So you pull the coil, you push the coil. The next video you will see what happens if there is circular motion of a coil. Fair enough?